In this video, I'm going to talk about LQR, which is linear quadratic regulator. So in the previous lectures, I talked about for linear time invariant system and how do I design the state feedback control, and also if the state is not available, how we design the state estimator and use the estimator in the control design. So here I'll talk about the in this video I talk about the case when we have the problem which is how to select the optimal gain under a certain metric. Okay, that's called LQR problem. So we start with the standard linear time invariant system given by x dot t, which is equal to axt plus b ut yt cxt. So here I drop the d plus ut because that can be simplified by subtracting yt from the dut. Okay. Now the standard state feedback control algorithm is given by ut, which is r minus kxt, assuming here r is my reference signal. And if I don't have the state, the actual state xt, so I can use the estimated state also apply to the state feedback control law. So basically I have ut, which is equal to r minus kx hat t. So x hat t here is this is called estimated state. So in the previous video I talked about two ways to estimate state. One is called open loop state estimate, one is closed loop state estimate. So the closed loop state estimate has benefit of guaranteeing that the state estimate error will be equal to 0 as t goes to infinity if the system is controllable. And if I talk about the closed loop state estimate, the state estimate is given by this: x hat dot t is equal to a times x hat t plus b ut plus l times yt minus c x hat t. So this form, the way we derive this form is given in the previous lecture. So the previous video, you can check how to derive the state feedback, the closed loop state feedback for the linear time invariant system. So the first question we have is, how do I pick the k? So we can pick different k, and they can satisfy some desired performance. For example, I want xt to be stable, to be bounded, for example. So I can select many different kinds of k, right? So here let's consider a special case when r is equal to 0. When r is equal, basically we have ut is just become negative kxt. So this is called a regulator problem. I just want to regulate my basic state. I want my xt goes to 0. Okay. The reason I consider rt to be 0 because I can, if I have r goes to any number, 10 for example, I just have to change a variable to be changed to k. If I want r to be 10, I just want to say ut is k r divided by k minus xt. So basically you can do a change of variable. If I change my x utility is r minus k times xt, now my goal is become to drive my x utility to be 0. Okay, so it always can convert to a regulator problem. That's why we consider this as a special case. When we have r is equal to 0, it's called a regulator problem. So for this case, let's take a few examples to see, hey, how do I pick a k? Okay. Let's say I have 4 different options for different k. Assuming I have a 3D, the state space is three-dimensional. So my k also is a three-dimensional one, like this, given by this. So let's say, assuming I have a k1, if I select k1, the k is a k parameter. So k is, let's make it not make it confusing. If I select k to be 1, 2, 3, okay, and my eigenvalues by computation of a minus bk, eigenvalue a minus bk is given by -2, -3, -1. This is for first option. So, and the b is, so here I assume for some a and b, of course, for some a b, and if I select k to be 1, 2, 3, this is a row vector. So I get an eigenvalue a minus bk to be -2, -3, -1. If I select k to be 2, 0, -1, the eigenvalues of a minus bk is -1, -1, -1. If I select k to be 5, 6, 7, the eigenvalues of a minus bk is 5, -5, -6, -3. If I select k to be -1, 3, -2, my eigenvalues of A minus BK is negative 1, 0, 1. So my question is, which ones are acceptable and which is not is best, for example. So the criteria for acceptor 1 for the regulation problem is, at least I want a system to be stable, right? I want a system to be stable, which means I don't want a state to go to infinity. But my goal is to, I want xt goes to 0, so I don't want xt go to infinity. That's not design. That's not acceptable. So if I'm going to use, assuming here I do know the state, okay? So my state feedback control algorithm is given by ut is negative xt because r is 0 here. So if I just substitute u by its feedback control law given by negative kxt, so my x dot t is axt plus b times negative kxt. So I just replace ut by negative kxt, which is given by a minus bk xt. So because I want this xt to be at least bounded, I'll go to 0. So I want because the solution here xt is e minus a minus bk times t times x0. So basically you want eigenvalues of a minus bk to have negative eigenvalues of a minus bk must have negative real parts, right? If you have the positive real parts or 0 real parts, xt will not go to 0, right? So at least I want to make sure that my eigenvalues of a minus bk to have negative real parts. So if we check the three options, a and b and c, for a and b and c, the eigenvalues are all negative, which is fine. So which means they are acceptable. A and B and C, they're all acceptable. You can choose anyone. They can guarantee that xt will go to 0 as t go to infinity. However, these not desirable, acceptable because one of eigenvalues is 1 polarity, which will drive the state to infinity. Okay. Now the next question is, which one is the best one? Like I have A and B and C. Probably I have even more options than A and B and C, but which one is the best? Okay, so when we talk about the best, we typically talk about the criterion. Like what criterion are we talking about? Okay, so let's say one of the typical way we think about this is, hey, I want my control input to be small, because for example, if you drive a car, you don't want to give a large force because you can cost a lot of energy. So one of the criteria is, hey, how can I check the control input to see, well, which one require less control input? So probably I want to select that one. Okay. So if you check this ut for A and B and C, now for the first one, assume of course the state is a three-dimensional state, x. So the k is, for A and B and C, we can compute the control input out in this form, specific form. So for A, because k is 1, 2, 3, I can compute ut is negative kx, which is negative 1, 2, 3 xt. Assuming here my state is x1t, x2t, and x3t. So I can compute the form of the ut, which is given by next x1t plus minus x2x2t minus 3x3t. I can also select b and c out in this way. Okay, so typically we do this one. If I consider this one, now if I have the same x1, x2, x3, so it looks like possibly c will have a high control for same state, because for example, if x1, x2, x3, they are positive, so this guy, the input, the absolute value of ut is higher, it's pretty big, right? Let's say, for example, x1t, x2t, they all, let's say if x1t is 1, x2t is 1, and x3t is 1. So here is negative, the absolute value is absolute, the input is 18 basically, so it's pretty big. If I compute this for the B case, its value will be just this is for C, right? For B, the input will be just negative 2, it will be just 3. The absolute value of ut will be just 3. For A, the absolute value will be just 6. So typically B is more desirable, of course, in this case. Okay, at least from the control input point of view, if you want the control to be small while still guarantee that xt will go to 0, so probably B is a good option. Okay, so this is one criterion people typically use. The other criteria is called transition performance. because we know that if you for certain UT and it takes a longer time for it to saturate, even the UT is, yeah, it is small, for example, for B, but it could be the case if you use UT, it takes a lot more time, much longer time for it to stabilize at a certain value, for example. So this will cause problem when we have, okay, let's move this one to here to make it a little bit. So this is my T, okay? So once you have this one, so for different the control input, you might have different transient profile, which means it may take a little bit longer time for you to stabilize to 0. So which is not desirable. For example, if I want to drive a car, I want to drive my car, right? I want to drive my car. I want to change lane, for example, from the current lane to the next lane. So typically we want this transient to be as smooth as possible. You want to change the lane as fast as possible, but we don't want this happen to be like this, oscillate a couple times and stabilize this lane, which is not desired. So typically we also want this transient, the state, the change of state, or electrical state can be pretty small. So which means I want this one to drop to 0 very fast. For example, probably the now this one works the best because it goes to 0 and it stays there pretty smooth. Okay, so typically there's a number of metrics we can use to quantify the which one is the best option. Okay, so in this one, for the LQR linear quadratic regulation problem, so what is a good metric to categorize the control objective? So typically, for the LQR problem, our goal is to keep the state small, because remember reference 0. So I want the state to be small enough. I don't want it to oscillate, to be small enough. Okay, so if you start from here, you go to 0 very fast. If I'm still going here, I want it to go to here very smooth. So gonna keep it very small as possible. Okay, I don't want to have oscillation. Basically, oscillation will cause more problems. Also, I want to reduce the control energy. Basically, I want the control input to be small. The smaller the better. Okay, so for the LQR, so this is also typical. What a typical metric people use to quantify if a control performance is good or not. We want to keep the state small, close to the desired. To drop the desired or increase the desired as fast as possible without oscillation. We also want to reduce the control energy as much as possible, which is very intuitive. Okay. So for this case, we can consider the next problem, how do I quantify it, right? I know this metric, yeah, I want to keep the state small, I want to reduce energy. So what is good cost function? Because I want a mathematical formulation of the metric. So metric is a mathematical formulation metric is given by cost function, which is given by J, called cost function J. It's integrated from 0 to infinity. We try to compute some integration from 0 to infinity over dt. So inside this one is called xtq xt plus ut r ut. So this is the first one is called penalty for the state. So basically I want to reduce this j. So this is a penalty for the state. The second one is a penalty for the control. Because I want to reduce this state, I want to reduce energy, control energy basically. And so what is this Q and R? So Q and R basically is a most popular choice is Q is given by a diagonal matrix, and each entry is non-negative. It can be a 0 if you don't care about, and I'll talk about the criteria to select this Q and R. So typically you want to have a Q to be a diagonal matrix and R to be also a diagonal matrix. So if I have xt to be equal to x1t, x2t, so on xnt. So the first term over here is given by x transpose t q xt. This is just given by summation I from 1 to n qii time xi t squared. So this is a summation of the squared of each state times qii. That's what's happened to the first one. Similar first one, second one, if my, let's change a different one. This is m, this is m. So if my use of t is u1t until umt, so the penalty for the u is given by ut transpose time r times ut is basically given by summation I from 1 to n is RII time UIT squared. So basically we want to compute, this is, we consider the penalty if I want to minimize. So I want to minimize, if I want to minimize this J, for example, I want to find a U that can minimize my J, which will minimize this XI, minimize my UI. So that's the goal we want to achieve. But we use cost function to characterize which metric we want to use to find the best U, or which is also means with best K. Okay. So this is called a linear quadratic regulator problem, or LQR problem. So this is a formal definition of the LQR problem. If I give a linear time invariant system given by x dot t, which is axt plus but, yt cxt, and the problem is to choose k such that using this feedback control, the state feedback control, ut is negative kxt, minimize the cost function j is equal to integration of 0 from 0 to infinity of st transpose times q times xt plus ut transpose r times ut over integrate over dt. So this is try to calculate the penalty for xt and ut from t is 0 to t is infinity. That's what the j cost function is trying to compute. So this problem is called a linear quadratic regulator problem, or LQR problem. So mathematically we can write this one as k star is equal to minimum of this cost function of k, which means I want to find a k that minimizes this one, then I assign this k to be k star. Okay. Of course, this one subject to my dynamic, which is given by x dot t is equal to ax plus but, and yt is cxt, ut is negative kt. I can drop this yt because that's not related to what we're trying. So this one you can just ignore this. So you have the linear system given by x dot t, which is ax plus but, and ut is equal to negative kxt. Okay. So that's my formal definition of the LQR problem. The LQR problem is trying to find the optimal k that can minimize the cost function j defined by this, subject to the linear time invariant system given by x dot t equal to ax t plus but, when ut is equal to negative kxt. Okay, so as I mentioned before, j is a cost function that penalizes both the state and the control input. Okay. For example, if I give you a linear time invariant system x dot t equal to 0, 1, 2, 3, 1, 5, negative 1, 0, negative 3 times xt plus 1, 2, 3, 1, negative 0 times ut. So basically I have this xt is three-dimensional one, x1t, x2t, x3t, and my ut is two-dimensional one, is just u1t and u2t. So that's my k, my xt and ut dimensional. So there are a couple of choices. Of course, I can select different choices for the cost function. For example, I can select j1 cost function j to be integration of 0 to infinity. This is always true. This is always the same for all cost functions. The form is always the same. And this also is the same. The this transpose, xt transpose xt, ut transpose ut. The only difference is the choice of this q and r. This is my q. This is my r. This is another q. This is another r. This is another q and another r. Okay. This is another q and another r. Okay. So let's say I can make different choice of this q and r. For example, j1 we select q to be a diagonal matrix with diagonal entry to be 1, 1, 1. And R is also diagonal matrix with diagonal entry to be 1, 1. For J2, I select the diagonal entry for Q to be 10, 10, 10. For R is also 10, 10. The J3 is for Q is 1, 1, 1 as a diagonal entry, and R is 10, 10. J4 is 10 for Q is 10, 10, 10, and R is 1, 1. So that's a different. We can swap it. So okay. So my question is, do we obtain the same K optimal? I should say K star. The optimal k star for the four different choice of my cost function. Okay, the answer is for J1, J2 they are the same. The reason that's the case is because I can rewrite the J1, J2 to be, if I pull the 10 outside, so it's just 10 times J1, okay, because the 10, if I pull the 10 outside, this become 1, 1, 1, this become 1, 1, so it's the same as G1. So if I minimize 10 times J2, well, I can pull the 10 outside, it's the same, the K, it's same as the minimize of K over J2. Sorry, this is 10 J1. This is J1, that's the same. That's why this is 10 J1 is J2, so yeah, that's the same. So for J1 and J2, they're the same. But if I use J3, J4, J1, J3, J4, or J2, J3, they are different. So they're not the same. Because the reason is because here you sort of consider this as I penalize. If I use a 10, 10, 10, I penalize them more. But if I want to minimize, let's say if I want to minimize J4 over K, so I want to select K because I mean for the same state over here, this gives me a higher cost. If the state is, let's say 1 or 1 or 1, this will be higher. This will be higher than if I use this Q as 1, 1, 1 over here, because this will give me a small penalty. This gives me a larger penalty. Similarly for R, this will give a larger penalty if I use a 10, 10, rather instead of if I it's a higher penalty than the one if I use 1, 1 in my R matrix. So when you meter that, you penalize this X differently. That's why the K will be different. Okay, if you select the same K, now this cost may be much higher than this cost. Okay, so next question, how do I choose K, Q, and R? Okay, so as mentioned before, the typical choice, the structure for the Q and R is given by two diagonal matrix, which means we only have the non-zero entries as a diagonal entries on Q and R, while other off diagonal entries are all just zero. Okay, this is the same for the Q and R. So this is a general guideline for selecting K, Q, and R in the LQR problem. So if I want to penalize, so these are four criteria. The first one is if you're making QII larger, then it causes X1, XIT to be small, which means that's pretty intuitive. Because if I say, hey, I want this Q22 to be large, this is 100, and this to be 1, this is be 1, right? They are all to be 1. Only Q22 is 100. So if I write down this J, integration from 0 to infinity, the product will be, you have x1 t squared times q11. q11 is 1 over here, times 1, plus x2 t squared times 100, because you have now you do so on and so forth. I just ignore this. You also have r term. Okay, this u term. Okay, this is u term. You do this dt because you want to do a lot of penalty on x1t, which means for the same x2t, the cost is much higher. Let's say x1t is 1. Now this is give you cost only 1 over here, right? Because x1 squared is 1 times 1 is 1. However, if I only have x2t is also 1, now your cost will be just 100. It's much higher than this one because the weight is like different. Which means if I want to penalize this one, I want it to be, because my goal is to minimize this. So this is not desirable. I want this state to be small, basically, right? So that's why if you're making this QII larger, which causes XI to be small, okay, eventually be small. You want to make it smaller. If you make your RI larger, so you want to cause UIT to be smaller. Okay, that's the goal. Okay, so if I draw a picture of that, so what's going to happen is T over here. I draw two cases. So this one is if you select Q, this is for QII. This is 100. If you start from here, you sort of see the state looking like they drop really fast. Okay, but if you select QII to be 1, for example, you could see something like this. This is for state. This is for state XIT. Okay, that's the difference. Okay, if you put large penalties, your state will drop much faster. If you put smaller one, you will have a larger state. Similarly for UT, if you do this one, okay, if you do this T, if I do this is my use of T. Okay, so if you have RII, which is, let's say 100, you will see something U is drop really fast. Okay, if you have, let's see, RII, which is 1. So you probably can see something is something like this. You probably have larger because you don't penalize too much on that. And if your QI is equal to 0, which means you don't have penalty for XIT, it doesn't matter. You can have oscillation, you can have whatever you have. If RII is equal to 0, you don't have penalty for UIT, which means you can. This one means you don't care how big XIT or UIT can be. So this is the only case. For example, if you don't care about UIT, which means you have a lot of input. You don't care about how big input it requires. Okay. So now we ought to go over the formulation of the QR, which means, hey, I want to find the optimal K that can minimize the cost function given by this form. I also talk about how to select this Q and R in the cost function based on our desire. For example, if I want some state to be much smaller, so it's better for us to give a large QII for that state. If I want the control input to be small, I want RI to be small. To be big, okay? Now the next question is, how do I obtain this K star, right? What is the optimal? Yeah, it looks like pretty good, right? So how do I find the optimal K star, okay? Now the answer to this question is the optimal K is given by R inverse B and P, okay? And well, R of course, so B already known, right? B is already defined here, and P is already defined over here. So R is given in the matrix over here. We define what we selected. So this R and B already known. So the P satisfies this equation. P times A plus A transpose times P plus Q minus P B R inverse B transpose P. This is 0. Of course, this is a zero matrix. It's not a zero scalar. It's a matrix. It has the same dimension of time P times A. Okay. So this one is called, so this equation is called algebraic Riccati equation, or simplified as, abbreviated as ARE, okay? So it only say if we can solve the equation, find the P, and if we compute the R inverse B times P, now we are done. So there's one assumption over here, because we need to compute the R inverse, okay? We need to compute the R inverse over here. So this says, okay, you cannot have, if I assume R is a diagonal, is R11, R22, RNN, RMN, which means each RI has to be positive, it cannot be negative, right? If it cannot be 0, if it's 0, you don't have an inverse, which means in order to solve the ARE, actually I cannot have 0 penalty on UIT, otherwise I cannot find the optimal K star, okay? Alright, so this is how we solve it, okay? Now this one is pretty complicated. I'll talk about later on how you find it using MATLAB, because there's a mathematical tool you can use, okay? So typically numerical solution can be really tough, okay? So how do I find a solution? When does the solution to this ARE? Because eventually it's important to find the P, otherwise I cannot find the K star, right? For the optimal gain, right? So when does the solution to ARE exist? So the answer to this question is if A and B is controllable, which means if the rank of a controllability matrix is equal to n, this n is dimension of xt, a solution to ARE, the algebraic Riccati equation always exists. So as long as A and B is controllable, we're okay. Okay. So next question is how to compute a K star. Okay. So typically it's a little bit hard because the P is multiple dimensional. It could be a square matrix basically. So it's a little bit hard to compute that one. So but we can use MATLAB to compute the solution directly. So in MATLAB you can use the command, it's called KPE. So this will return K and P and E. You use a command called LQR, and you give this is how you specify A and B and Q and R. Okay, now you'll be able to compute they will return the K and P and E. So this K will be the K star. You already computed for you K star. This P is whatever is the P we need over here. This E is returns the eigenvalues of A must be K. K star to use A must be K star. Okay, so I already computed for you. Okay, so once if I give you a homework or give you a question on this one, you just have to use MATLAB to input the LQR command to specify your A is C is 2012, for example. B is, let's say, 12, for example. And Q is 1002, and R is 2001. You just can input those matrices, and then you just say, hey, K and P and E equal to LQR, or this ABCD, ABQR. Now you are done. You will return the KP value. Okay, so as a summary, so I talk about give a linear time invariant system consists of regulation problem, which means my R is equal to 0, and the cost function is given by J, which is integrated from 0 to infinity xt transpose time q time xt plus ut transpose r ut dt. My optimal control input ut is given by negative k star times xt, and the negative k star, the k star is given by this, I mentioned here in the previously. So my optimal control input is given by negative r inverse bp xt, and the k star is the solution to the another solution, k star. So P is the solution to the ARE, solution to the algebraic Riccati equation.